This somewhat provocative title has to do with a little amusing inference task that you can do in quantum mechanics, which I think has some foundational significance. So what I need to do first is discuss or define operationally what I will be calling joint measurement. We start with the standard quantum textbook measurement. Okay, so we have this black box, it has a pointer, and let's say we're measuring some observable A of a system. So this we can represent using a quantum circuit, for instance, by coupling the system to some other device that we call the measurement device or instrument through this unitary coupling. So it's basically phase space, or a translation operator that is valued on the operator that you're measuring, and the translation operator is translates this variable pi that we call the pointer variable, and q is the conjugate. So if, for instance, psi is the eigenstate of A, then you get a precise shift of the pointer variable. So with that, you can you can extend this notion operationally and say, okay, well, let me define a joint measurement as a situation where now I'm going to have, let's say, I'm going to measure two observables, A and B. So I'm going to have two pointer variables, and they're going to be essentially the conjunction of the two measurements. The two apparatuses are going to be coupled at the same time. And so you have two measuring devices, a unitary operator that is the extension of the previous one, and then two pointer variables. And of course, I mean, there's no, in the repertoire of quantum mechanics, we don't have, this is usually not the type of thing that we talk about, but it has been discussed. And you can relate that to, standard results with the canonical or the uncertainty relations. So if we're dealing with the canonical uncertainty relations in particular, they are defined in terms of measurements that you perform one in exclusion of the other. In other words, we either perform measurements of X or measurements of P, and then we look at how the variances work. And we know, of course, that the product of the uncertainties has to be larger than h bar over 2. You can also do the same analysis with the joint measurement. Okay, and this has been done by Arthurs and Goodman, and it's actually quite interesting. So what you end up finding is that the uncertainties in the respective marginal distributions, they're bounded, lower bounded by h bar, not h. Okay, and heuristically you can think of that result as being the combination of two uncertainties, or two bounds. One factor of h bar 2 that's coming from psi, and then another factor of h bar over 2 that has to do with the simultaneous back reaction from one measurement device to the other, to the variable that's measured by the other one, and vice versa. So, it seems to give you the idea that certainly there should be no way of undoing that bound. Now, so the inference problem essentially is the following. Let's say you have Bob here, and what Bob does is he gives Alice a canonical system, and she is going to be in some black box and measure simultaneously X and P, and then she gives back the system to Bob. Okay, and the task for Bob is to infer precisely what the outcomes of these measurements were. Okay, and you can either think it's an unsolvable problem in quantum mechanics, or it's trivial. It would be trivial, for instance, if Alice were measuring first X and then P, because in that case, if Bob knows that, and he can prepare the state in an eigenstate of X, and then finally make a measurement of P, and he can infer both readings. But we're talking about the simultaneous measurement, so we have this problem of the back reaction between the two instruments. And the suggestion before was that this is actually bounded by h bar over 2. So what's interesting is actually that you can do it, you can solve the problem, and in order to do it, what you need to do is you need to include entanglement. as well. So Bob, what he needs to have is another canonical system, and I'm calling it a prime system, x prime and p prime. And then for this combined system, he can define two collective variables. So it's basically like a 45-degree rotation of the variables of the axis, something like this. These two linear combinations, x plus and minus, p plus and minus. And then what he'll do is as follows. He will pre-select his combined system by making a measurement of x plus and p minus. And finally, his post-selection at the end, when he gets the system back, is make a measurement of x minus and p plus. And what turns out is that effectively, when you have those two boundary conditions, for the purposes of the instruments, okay, you can replace in that unitary operator that's acting there, you can replace the x and the p operators by c numbers. What I call x tilde and p tilde. And they're just the linear combinations of x plus or minus or p plus and minus that you get from these boundary conditions. Okay, and that's actually quite easy to prove. What you need to do is you need to look at phase-space translation operators, so operators of this form, okay, and what we can show then is that the weak value of those operators, or that family of operators, it's a two-function family, two-parameter family, u and v. Okay, the weak value of that operator is essentially as if you had just replaced the q numbers by c numbers. And the way to see it is very easy. You look at the exponent, so you have ux plus vp. U and v are the c numbers. Now what I'm going to do is I'm going to take x and p and I'm going to rewrite them in terms of my x minuses and p and x plus minus and p plus minus. Okay, and I regroup them in this way. So I have, so I regroup a minus x with a plus p and a plus x with a minus p. And so you get these two operators, and then you can show that these operators actually commute. Okay, so if you commute, you can disentangle the exponential, and then they connect on both sides, and they give you, the result that we were discussing. So there's actually a very interesting implication to this whole thing, and it's that these phase-space translation operators appear in the mapping of phase-space functions to quantum operators through what's called the Weil mapping, or Weil ordering. So it turns out as a consequence that so with these two dots, basically what they represent is Weil ordering, that if you look at the weak value of a phase-space function, it turns out to be the phase-space function itself evaluated at x tilde and p tilde. Okay. So with the same boundary conditions, you get the phase-space function evaluated at the same phase-space point, okay, without any, let's say, fluctuation terms or anything like that. Okay, so I'll conclude right. So so basically what we're saying is there exist initial and final boundary conditions that allow you to make a precise inference of a simultaneous joint measurement of two non-commuting observables, x and p. And for the same boundary conditions, you can show that weak measurements, or weak values that are obtained there, they essentially give you the corresponding phase-space function evaluated at those inferred values, x tilde and p tilde. So I think the final conclusion is that there's something very interesting that quantum mechanics may be telling us, and it's that with post-selection and entanglement, it may be possible to build a classical description of a point of phase space. And